Welcome to Chapter 8 of the C++ programming language by Bajan Strustrup. Today we are looking at structs, unions, and enumerations. So from the last two chapters, we've been looking at different types of things, right? From Chapter 6, we saw that big Venn diagram with all the types. And Chapter 6 and 7, we've been sort of ticking off some of those types. Today, we are looking at the user-defined types. Now, there was one circle labeled user-defined types, which included the structs, unions, and enumerations. Within that, there's also classes. Within the user-defined types, there's also classes. But classes is a pretty loaded thing, so the textbook has its own kind of section for that, so it's not discussed in a lot of detail here. Alright, yes, let me just start. So, introducing what we say are the user-defined types. So, what user-defined kind of suggests is that you, as the programmer or as the coder, are the person creating the type and giving some sort of definition or providing some sort of definition. So just to give like a quick explanation of what each one is. So structs are sequences or a sequence of elements of arbitrary type. Unions are a special type of struct. So it's a struct that holds the value of exactly one element at any one time. An enum, short for enumeration, is a type with a set of named constants, or we also say enumerators. Another word for the constants we're talking about. So there's an enum is short for enumerations, and then we also have enumerators, which is the same thing as the constants. And then we have enum class, which kind of extends from enums. It's a type of enum where the enumerators are within the scope of the enumeration, and there's no implicit conversions, in type, I assume, to other types. So no implicit conversions to other types are provided or allowed. So that's a quick overview of basically what we're going to be looking at. How is that? A bit small, alright, bigger. Anyway, yeah. So those are the types we're going to be looking at. And in terms of, I guess just to give a couple extra details, when we look at these particular user-defined types, we generally consider them more C-style programming, especially, I would say, structs. Because classes kind of extend from structs, a lot of people would say that structs are more of a C thing than a C++ thing, but they're still quite useful in certain cases. And they all focus on the representation of data. So the focus of these types are on representation of more abstract data. And just a final note, I guess I mentioned this, but structs are a simple form of a class. So especially in our discussion about structs, you can consider it as structs are a simple form of a class, is what that says. You can consider the introduction to structs as kind of a small introduction to classes themselves. So that's how I would introduce this. Basic definition of what we're looking at, of each of the types we're looking at, and then we'll get into more detail. So we start with 8.2. Well, we didn't start, but we continue on to 8.2, which is called structures. And bear in mind that struct is short for structures. That's it, structures. So a struct is an aggregate or a combination of elements of arbitrary type. So I think when we start, especially when we get to these kind of user-defined types, we go through a lot of examples because it's just easier to show how things are done. Like elements, that says aggregate of elements, that's what that says. I keep forgetting about the light. So we can define a struct, introducing one with the keyword struct, and then we give the struct name. So the example I have is person. So by doing that, I've created a struct called person. And then you would provide a bunch of members or fields. So you might give a const char star name. So this is almost as if I'm declaring a variable, like const char star is my type, and then name, right? Like this is us sort of declaring things almost. Int age. Notice the semicolons as well. Bool likes cats, and double height. I have one more, which is address, and then my address. Okay, so just to break down what we're seeing here, I have created a struct called person. That's what's happened here. Then I provided the fields that are associated with the struct person. That's what it means by a struct. This overall struct is an aggregate or a combination of elements. Each one of these is an element, right? Name, age, likes, cat, height, address, of arbitrary type, whatever type you want, whether it's const, char, star, int, bool, double, or address. Address isn't, obviously, address is not an inbuilt type, but the point of address is, address would be some other struct defined previously. So the idea is we can have structs in our struct, right? We can, as part of our elements, we can have a struct as one of our elements. Okay, so we have whatever types we want in here in order to define our struct. And notice each element ends with a semicolon when we do defining, and even at the end of this brace here, the squiggly bracket, there is a semicolon there. I'm not sure if that's really clear, but that's a semicolon. Okay. Now let's say we wanted to, maybe I'll keep the example. Let's say we wanted to create a variable of type person now, right? Because the struct is person. So in our main function, so this will be outside our main function. Inside our main function, we would have int main, right? I'm not sure if I've ever talked about the main function in detail. In essence, the main function is the entry point for a C++ program. When you run a program, your execution starts within the main function, just arbitrary, like you know that for a fact. Let's say I have this, we'd have return 0 at the end normally. If I wanted to create a variable of type struct person, I would do something like person, and then something like that, and then the identifier, like new person. So what's happened? It's within my main function, I've provided the type, and then I provided an identifier, like as you would with any other variable, right? Int age or int x, semicolon in the end, of course. You give the type person, which is the user-defined type, the type that we created, which is of type struct. The type person, and then the identifier. Accessing a member requires the dot period, the full stop operator. So if I was to do something like new person, full stop or period, the dot operator, and then name equals, and I use a string that will bob below, right? I am accessing the field name for person using the dot operator and assigning, in this case, assigning the value bob hello to the name field of the new person. So just to write that out. Accessing a member or element requires the dot operator. So every time you create a new person, they get their own sort of unique set of fields that you can sort of manipulate and access using the dot operator like this. So if I then ask to print new person dot name, right? I would access specifically new person, the one we created up here. I'll access them and then access the name specific to that new person. So it would print Bob hello in this case, right? Because I assigned the value Bob hello to the name. Now initialization, right? This is one way we could technically initialize, declare the variable, and then for each field give an assignment, give an initialization. But we can actually do that in a slightly slightly more streamlined way, I guess, using the braces notation, the squiggly brackets notation. So instead of just declaring something with the semicolon at the end, we can actually do something like equals, put a squiggly bracket, put another squiggly bracket, and then literally just put in the values Bob hello for the name, right? Const char star. Remember, string literals have type const char star. Give a name, we can give an age, like I've written 102, which is a bit silly, but we can put true for the likes cats, and we can give a double like 74.2. Forgotten these values I put, and I'm not going to bother with the address. Just pretend the address isn't there right now. This was just to explain that you could put structs in there, but I'm not going to bother with that right now. But what's happening is the new person that we created of type person is going to have a name with the value Bob hello, an age of value 102, a boolean variable likes cats with the value true, and a double height with the value of 74.2. Right, so that's what's happened. If you were to access any one of these elements using new person dot age dot likes cats, you would return the corresponding value. Okay, so yeah, we can use the initialization, the braces notation for that. Pointers to structs. So last chapter we talked about pointers, and like just about everything in our programs, structs will exist. Variables of this particular struct type will exist in memory with a particular memory address, and so we can get pointers. We can access that memory address. So pointers to structs. So I guess the first thing to bear in mind is the address, or the memory address, of a struct, when we get the memory address of a struct, actually refers to the memory address of the first element, or the first byte of the first element. The memory address of the first byte of the first element. So I'll make a simpler struct. Let's say we have something like struct coordinate. Coordinate's good. Struct coord, and we have like int x and int y. So this is outside our main function. We just define that. That says coord, short for coordinate. And then within our main function, we have something like coord new coord equals, and then we say 5, 3. Right? So this is the top thing is outside our main function, and this is inside our main function. We've created a new coordinate with values 5 for x and 3 for y. If I was to get, in memory I should say, sorry, if we were to draw a memory for this, some memory address will be chosen. We would need 8 bytes, because 4 bytes for the first integer, 4 bytes for the second, and I'm just going to do this for now. Pretend each block is 8 bytes, pretend each block is 4 bytes. The 5 would be stored in the first block, the 3 would be stored in the second block, and if we were to get the address, if we were to do ampersand new coord, get the address of this guy we created here, it would get the address of the first byte of that 5. The first byte of the first element is the x value, is the 5, is that guy. So we take the first byte and get its address, and that would be the address of the overall variable. That's what that would return. So because we can get the address of a struct in this way, it's defined, we can declare a pointer. So we can declare a pointer like person star pointer, PTR will say, equals ampersand new person. So I forgot that I brought back the person example, but essentially it's the same as anything else. We said, remember, with integers we would say int star whatever equals ampersand and then some integer x, for example. It's the same thing. Instead of int, we have person, that's the type. Person star, because it's a pointer, then our identifier, pointer in this case, equals, and then we take the address of the actual struct variable that we created before. Maybe I should just rewrite it quickly. Before we had person, new person, equals, and then we had, all that stuff, right? With the Bob hello and the age and whatever. We created a new person. Now we're getting the address of that new person and assigning it to a pointer of type person star, right? Just like our int star, but this time with the user-defined struct. Now, we can access members via a pointer using the arrow method, the arrow operator. So it's a hyphen followed by a greater than symbol. So if I was to do pointer arrow name, and I was to print it, for example, if I was to print this pointer and access the name, it would give me Bob hello again, right? Because without necessarily needing to use the dot operator on new person, I'm using the arrow operator on the pointer to access the field instead. So the arrow is basically capable of dereferencing and then accessing. So I guess if I was to give a more explicit version, so when we do pointer and then accessing some field like name, when we do that, it's equivalent to taking the pointer, right, dereferencing it using that star operator, if we remember, and then using our normal dot operator to access the name. Because when we dereference, we're essentially getting back the new person object. We're getting back that original new person object. And then we access name as we would normally with the dot, as opposed to the arrow. Right? So the arrow is, I have a pointer, I'm going to use the arrow on that pointer to dereference and then access a field. Whereas if we've already dereferenced it using the star, we would just use the dot operator. All right. We can also use references, right? Once again, like especially if something exists in memory. Generally speaking, we can get a reference to it, so long as we can access its address. So if we were to do person, and instead of star asterisk put ampersand, r for reference equals again new person, right? So we got the original object, new person, and now we have created a reference, an L value reference, to a new person. And because when we use references, we kind of almost pretend that they are the objects they're referencing. We access members by doing, for example, dot, and then, for example, name, or whatever the field name is, right? Name, age, whatever I said, likes, cats, etc. Whatever the field you want, use a dot. Because remember, operators are never applied on the actual reference, but rather the reference is dereferenced first to access the original element, and then operators are applied on that element instead, on that object, not on the reference. So we use the dot operator for references. Now, we haven't really talked about the equality and inequality operators, but normally when we want to check if two things are equal, for example, values or addresses, we use the double equal sign operator. And to check if two things aren't equal, we do exclamation mark equal sign, which means not equal. It's almost like it's equivalent to like this symbol, where you say not equal to. Both, so this means is equal to, this means not equal to, and you normally put two things on either side, either here or here, or like here and here, to check if two things are equal to each other, or to check if they're not. These operators are not by default available for struct variables or struct objects. If I make new person 1 equals person and then do my initialization, and person new person 2, if I have these two new person variables of type person, I can't check their equality, so to speak, just by using the equal sign. And by check their equality, we normally mean check that their fields are the same. We can check if their addresses are the same, which can be helpful, but straight up checking if their fields are the same using something like the equality operator isn't available. But by default, I should say. But we can define these operators for a struct. So I believe this is what operator overloading is, or maybe it's just called operator. Maybe it's not overloading because it doesn't have an original definition. But it's something to do with being able to give operators new functionality. It's part of it. I think it's quite an important part of C++. So equal and not equal to are not available by default, and hopefully I'll have a snippet. I should have a code snippet to show that that's not available. But if you're able to redefine or give a new definition for those operators, then you can use them. All right. What am I up to? Okay. This is the part I'm a bit scared of. I hope to explain this in an okay way, but I can't explain it completely, unfortunately, because I don't even understand it fully. 8.2.1 Struct Layout. I will preface all of this. I'll preface this part by saying in chapter 6, I think it was 6.2.9, there's a section called Memory Alignment. And I chose to completely skip it because I felt like it was talking about details that didn't really make a lot of sense. It made sense for the chapter, but for what I was talking about, I didn't feel like it made sense. So I skipped it. Now that we're talking about structs, it's a little bit easier to talk about memory alignment, but in essence, memory alignment is a consequence of hardware things, hardware limitations maybe, or hardware functionality, which means if you really want to understand memory alignment and why it's important and why it's done, you almost have to get into the hardware level, which is not my field or my strong suit at all. So in my notes at the moment, there are layers of abstraction where I kind of just pretend I understand the hardware part, and I explain the consequence of why we do this memory alignment stuff. But it's definitely easier to talk about memory alignment now that we have this idea of structs and structs in memory under our belt. Okay, so we'll talk about this part first. Starting simple, members of a struct, or the elements, are held in the order they are declared. So in that previous example with the coordinates, right? I created the members are held in the order they are declared. So in the previous example with coordinates, we talked about like putting the x and the y both in memory, but we said that the x would be put in memory first and then the y. And the reason for that is because x was defined first in the struct definition, and then y was put in afterwards. So it would be done in that order. Now, however, due to this strange thing called memory alignment, some struct sizes may be greater than the sum of the sizes of the members. Now, what does that mean, right? Suppose I have a struct that I defined called weird size, okay? And in that struct, I have a short, right? Remember, short is a type of integer, one of the integral types. Short x and an int, normal int, y. Now I've defined that struct. Normally, it's expected that a short has 2 bytes. Right? If you were to do size of x or size of short, you would normally see it's 2 bytes. And size of y or size of int, you'd expect to be 4 bytes. Okay? But if you want to do size of my struct, right? Because size of it you can take in types as well as actual variables. So if I plug in that type my struct into size of would give you the number of bytes. You would expect size of to give you 6, because the struct contains 1 short, so 2 bytes, and 1 integer, 4 bytes. You would expect size of to give you 6 bytes, but in actuality you'll find, and I should have a program on this, it gives you 8. And we ask ourselves, well, where did the extra 2 bytes come from? And again, really going into the why is tricky, but I basically found, from sort of weaving through Stack Overflow, I basically found 2 rules that seem to kind of give a lot of explanation as to what's happening in memory, at least, even if you don't fully understand the why part. So the rules that I've found are, for a member of size n bytes, so some arbitrary integer n, that member, damn it, I realized halfway through I was too high, for a member of size n bytes, that member is placed in an address. It's placed in an address divisible by n. Okay. So what am I saying? I'm saying, for the short, it's divisible. It has 2 bytes, so it needs to be placed in an address divisible by 2. If I'm in a for the y, the integer, it has size 4, so it needs to be placed at an address divisible by 4. So to draw out memory, let's say I have memory like this. A valid place for the short to be placed in would be something like address 20, right? The short would be placed, would span, the short x would span across addresses 20 and 21. So x would take up that much space, right? So that's the 20 and 21. Now, in order to place the y, then, sorry, I've drawn this badly. This is address 20, and this is address 21, and this is address 22. So at first glance, you might think to place the integer at 22, 20, 21, 22. But from our rule, we're saying, well, because y is 4 bytes big, it has to be placed at an address divisible by 4. So 22 isn't actually allowed. So instead, we kind of skip across a bit, and we get to 24. 24, 25, 26, and 27. So 24, 25, 26, and 27. And y goes to here. And so address 22 and 23, we call them, what do we call them? I forgot now. Holes or padding, that's the one. We call them padding bytes. This is 22 and this is 23. (20, 21, 22, 23). And then at 24 is where y gets placed. So the red we call padding, right? It's bytes that have been put in to basically allow for this rule to be maintained. And hopefully we can see that x is at address 20, so divisible by 2, and y is now at address 24, which is divisible by 4. So that rule applies there. Right, so that's one rule. Now, for people who are kind of thinking about the numbers, might ask, well, what if instead of 20, we placed the short at address 22? Then we wouldn't need any padding bytes. 22, 23, 24, 25, 26, 27, I think. So the short would go here, right, at address 22, which is divisible by 2, so that's not a problem. and then this this integer would start at 24. I'm doing it in red, but this is just the integer. It's not holes, or it's not pattern. In this case, the red is the integer. And we've broken the rules, right? The short, the blue, starts at 22. The red starts at 24. However, this violates the second rule, which is I lost it. Where is it? The second rule that I found was the size of the struct needs to be divisible by the largest alignment requirement. Okay? What is the largest alignment requirement? The size of the struct, how big it is, needs to be divisible by this largest alignment requirement. Generally, I would say, like from what I can tell, it's basically the biggest element of fundamental type. That's what I can tell so far. Usually, and you'd expect it to be a power of 2. So, like, you know, in this case, the integer is the biggest fundamental type we have. So it would be, or maybe not fundamental. What's the one that includes pointers as well? I've forgotten now. Basically, the non-user defined types. You pick a type that is largest in there. So in this case, the integer, that's 4. So the size of the struct needs to be divisible by 4. You know, if your biggest thing was a short, right, then it has to be divisible by 2. If the biggest thing was a long, I believe that's 8 bytes. So then it would have to be divisible by 8. If it was an array, this is what it gets interesting. Let's say it was an array of integers, and there's 8 integers in that array. You might think it has to be 32 bytes, right? That's because 8 integers, each of 4 bytes. You might think that the size is therefore 32. But I believe we actually look at each individual element within the array as opposed to looking at the array in its entirety. And so the largest alignment requirement would still be 4, and so it would have to be divisible by 4. The size would have to be divisible by 4. So that's the general idea. So in this case, trying to apply that rule, you'd have problems because, you know, we said that the biggest alignment requirement is 4, but this is only 6. So we've broken that rule. I think I can motivate why this rule is important, because imagine you have an array, right? You have an array of 2 where each element is one of these guys. So this is basically one element of the array, and we're going to try to put another element afterwards, right? What we want with an array is for the elements to always be glued next to each other. We never want gaps in our array, because when we try to access elements, it's a lot easier if the elements in the array are like right next to each other. However, by rule 1, if we wanted to place the next element right in our array, this would be element 1, and we're trying to put the next element right after in our 2-size array, we would end up with something like this. This is the short, right? 29 and 30. And then I'm not going to bother drawing all 4 bytes, but then the integer starts, right? This obviously be 4 bytes big, but the start of the integer starts at byte 30. Remember that the integer has 4 bytes in it, but it's starting at byte 30, at address 30, which is not divisible by 4. So by not doing this rule, right, you actually end up risking breaking the first rule. Especially in the context of arrays, where you have 2 of them and you try to glue them together. The alternative option would be to try to have like a gap, so like you would actually start this guy here in your array, keep it 6 bytes long, but that would cause a gap between the 2 elements. And we never want a gap in our elements for arrays, because that messes up how array accessing works, like how indexes and stuff work. So, you know, if you try to, where is it here? If you try to shift this down by 2 bytes to make the short start at 30 and make the integer start at 32, it might seem okay, but then you'd have a gap in your elements in your array, and that would be a problem. So generally, we expect both these rules to be followed. That's what I found so far. There's probably other things in there, but those are the 2 rules I've seen. And why are these rules applied? It's to do with, like I said, it's to do with hardware. Specifically, we talk about this idea of boundaries, like memory alignment boundaries, word boundaries. This idea of, if you think of the integers that are divisible by your size as your boundary, like you have to lie on those boundaries. If you don't lie on those boundaries, if you spill across 2 regions, right? Maybe I'll draw it. Hang on. So let's say for integers, this address here, whatever it is divisible by 4, and this is also divisible by 4, right? And I'll draw it like 1, 2, 3, 4. So it wants, if you want to store an integer into here, it wants you to place it somewhere here. If you were to place it something like this, right, spilling across the boundary into 2 sort of regions, here and here, there's something in the hardware which isn't really able to sort of cut out between two boundaries or across two regions effectively or efficiently. If you had an integer, I'll color it in blue, if you had an integer that spilled across the boundary like this, for some reason, this is where I'm abstracting a bit, I'm not sure why, but for some reason, your CPU, I think, would have to read this region first and sort of cut out those 2 bytes using one memory access, and then read this region again, read this region next with another memory access and cut out these 2 bytes, and then do some clever bit manipulation, which is a separate thing, but some extra processes to basically extract out this bit of information and then recombine them together to make the integer you want. So, but bottom line is you have 2 memory accesses. If you're able to store your integer like this, again, within the boundary, your CPU is able to read within that region with one memory access, so it's more efficient. That's like as far as I understand it so far, this idea of like you need to stay within your boundary because then the memory access is less, like you can do it faster. But why the CPU has to read like this, why it can't sort of do it like why it can't read like this really quickly, why it has to always stay on the boundaries, I'm not sure. So that's as much detail as I'm willing to go in right now. I'm hoping one day I will have better understanding of hardware, of CPUs, of things like memory buses and data buses, and I know what they are properly, and the cache and all these exciting CPU things. I'm hoping one day I'll figure those things out, and then I can actually explain memory alignment in a way that doesn't have to rely on as much abstraction. There'll probably be still some levels of abstraction, but I'm hoping that I can get a bit more detail in. Okay, trying to figure out how long is structs. A bit left. Okay. 8 point. How long is time actually? Okay, not bad. So 8.2.2 looks at struct names. Now we looked at like the rules for names in general. I think in chapter 6, where it's like you can only use alphabet and numbers and underscores. You can only start with a letter or an underscore like that. The struct name follows those same rules, so I'm not going to say them again. But there is this other rule about struct names, which is a struct name or a struct identifier is available immediately after it has been seen. I hope I give enough space, but I could probably give a bit more. It's available immediately after it has been seen. So what is the consequence of that? It is legal and quite common in some instances to see something like this. Imagine you have a struct and the name of the struct is link, and I'm going to give it 2 fields. One field is a pointer to a link that I'm going to call previous or prev, right? There's a pointer to a link, that's a star, and my second field is another pointer to another link object, and I'm going to call that pointer next, and semicolon. So this is perfectly legal, okay? The compiler sees that. I wrote it up. The compiler sees that, and there's no problems with it because it has already come across the name link, right? It's happy to see it again without too much trouble. However, we cannot declare new objects. We cannot declare new objects of a struct until the definition is complete. What does that mean? So what clearly there's some kind of problem that I'm trying to introduce. We cannot declare new objects of a struct until the definition is complete. When we do something like this, we're essentially doing a declaration. We're saying this guy link is going to have a pointer to a link, right? Whenever you have a link object, that's going to contain 2 link pointers. However, what if I tried something like this? Struct link. Instead of using a pointer, I just straight up said, I'm going to store link previous and link next. Essentially with the same intentions of having access to a previous link and a next link, right? The same intention. However, the compiler sees that and has a problem. Okay? Has a problem with this, even though it was fine with this. From the board, it's because we tried to declare a new object. This is a declaration. We tried to declare a new object of the struct without completing the definition of the struct, right? But why does it really have a problem, right? Because we did something very similar here and it was fine. So why does it really have a problem with this? It's because of the size. The size of a pointer is always the same, regardless of what object you're pointing to. That's the beauty of pointers. So on a 64-bit machine, we would say a pointer is 64 bits. That's one of the characteristics of a 64-bit machine. 64 bits is 8 bytes. So a pointer is always 8 bytes on a 64-bit machine. On a 32-bit machine, pointer is 32 bits, 4 bytes, right? So it's always the same. So if I look at this guy, right, and I mean in this case it won't matter, but in general, I'm just going to forget about memory alignment for now, just when we talk about sizes of things. In this case it won't matter. If I'm talking about a 64-bit machine, I can tell you how big a link is. It contains 2 pointers, 2 addresses, that individually point to links, but I know that this, on a 64-bit machine, is going to be 8 bytes, and this is going to be 8 bytes, by looking through, right? Without having to do anything super fancy. So then overall, I can calculate that the size of the link struct is going to be 16 bytes for 2 pointers. Again, memory alignment won't be a problem there. Here, if, as part of your size calculation, you ask, okay, to define my link struct, I need to know the size of the link struct. But we haven't completed the definition, so there's no way of actually knowing the size yet, right? There's a recursive error here. I can't, I'm saying, okay, well, I know that the size of link is supposed to be the size of 2 links. Well, that doesn't make any sense. All of a sudden, the size of my thing is supposed to be double the size of itself, right? So you have a recursive problem. And I think even if you had something like this, where you're like, well, I know that link contains 1 link, in which case, the link has size link, which I guess isn't a contradiction. You don't actually know how many bytes to give. What is a link, right? How big is a link? I know how big the pointer to a link should be, 8 bytes, but I don't know how big a link is. So that's the real underlying problem. That's why we can't do this. Here I know pointers is fine, 8 bytes, 8 bytes. Here I cannot know how much memory I'm supposed to give to an object of type link on that side. Now we get into some cool weird stuff. What if we want 2 structs to contain each other? Right? In this case, we're able to make a struct contain itself using pointers specifically. But what if we want 2 structs to contain each other? So, if we want 2 structs to contain each other, one must be purely declared. And we should use pointers. So it's easy for me to write that out, but it's even better to use an example. So suppose I have 2 structs. And I have struct list, and I have struct link. And I want link as a struct to contain a list, and I want list to contain a link. So this is kind of like weird, like zigzag. Like link has a list, which then has a link, which has a list, which has a link, like that. So we have this weird kind of division. If I want to do something like that, I would begin by declaring one of them, purely declaring. That's what I mean by pure. No definition, just declaring. Because if I try to put a definition, I'd have to put list in there, but I don't know what list is yet. So I purely just declare it. Then I can define the other guy. I can define link in this case, sorry. So that's list over there. All right, bigger. List and link are too similar. Maybe I should use A and B. I thought that's easier. So if I have A and B, I don't know why I use link and here. I would define A first. I would declare A first. Purely just declare. Just say, this is my struct A. Then I would define the other guy. I would define struct B. And would say, okay, A star, and then the member, or the field name. Oops. And the compiler is not going to have any problems with that, because it knows what it's seen A before, right? Very first rule. If we see the name, we can use it. We're using a pointer, so we know the size, and we've seen that A before, so we know that this guy is going to be 8 bytes big on a 64-bit machine, and we've seen A, so there's no problem with that. And now we can define A. Struct, now that we've introduced B, we can define A. Struct A, and then we can say, what do we say? B star. B star member. And again, no problems. It's seen B before, and it knows that this is, the compiler knows that this is 8 bytes, so no problems. There is a slight question people might have regarding, like, how do you begin an object like this, in the sense that, like, you know that an A contains a B, and then a B points to an A, and then an A points to a B, and it's like, to what end? I believe one option is to make one of them point to the null pointer, because remember, null pointers, you can, any pointer of any type can point to the null pointer, so you can make, like, A point to B, point back to A, point to B. At some point, A might point to the null pointer, and then that could be the sort of terminating condition. You might also be able to make like a circular thing where like A points to B and then B points back to A, maybe. But it's definitely plausible to do something like this. And I think there's probably instances where you would do this. I'm not sure where, but it's probably somewhere. Some kind of zigzag effect. Okay, so in general, just to sort of really go through all the rules, what we've seen is if you're going to declare a struct without really giving it any kind of definition, if you purely just see the name of the struct, right, like that first rule, if you purely just see the name without any kind of definition, you can use that struct in any case where the size is unimportant. So if we just declare, so purely declare a struct S, right, some generic struct S, we can use S in scenarios where the size of S is not important. Unfortunately, as you might imagine, there's not many use cases where this actually works, because generally speaking, when you're working with a computer and it's trying to represent things for you, it needs to know the size of things in order to be able to represent them accurately. So there's not many situations where this works super well, but just list them out. So you can, of course, declare the struct S. We've seen that before without actually giving a definition. We can purely declare a function, right? We can just declare that function without giving any body. We can declare a function that takes in the S. It takes in a variable in an argument of. Sorry. We can declare a function which takes in an argument of type S. So I was trying to get at. And we can also do something like this, where we have like a function h which takes in a pointer to an S object and returns a pointer to an S object. Maybe it just returns itself or something, I don't know. But we can declare these things. Okay. Now, where things get a bit tricky is when we try to actually sort of use an object of type S. So this is a function that kind of like h is taking in a pointer of type S. Right, sorry, taking in a pointer that points to an object of type S. So we know the size of it because it's 64 bits, it's a pointer. We cannot create a variable a of type S. This will cause an error. Why? Because when we try to create a variable like a, the compiler needs to know how much memory to give to a. How much memory is a, that name a, in charge of? We do not know the size of S though, because we didn't define it. So we cannot declare variables. If we try to call f, right? Obviously, there's no body, so there's not even anything to really do. But another issue is even if f had something to do and returned something, we don't know how big the return value is in terms of how many bytes it's going to take. And when the compiler is trying to work with this, it needs to know how many bytes the function is going to be giving back to the caller, so we can allocate memory and be able to put the object in that memory so that the other object can see it. The caller can see that object. Without knowing the size of S, though, you're not able to allocate the correct amount of memory. So that's going to be a problem. Same thing here. If you try to do something like this, something like, even if, let's pretend that the object A over here was somehow successfully created, if you try to pass it into a function like this, right, which takes in an S object, that will also cause a problem, because similar to return values, argument values, when they are passed to an object, to a function, sorry, that object needs to be allocated memory so that the function can see the object, right? We talked about stack frames and we talked about sort of copying memory over in that sense. You need to know how much memory you're going to be copying. You need to know how many bytes are going to be there. So that's going to cause a problem. Naturally, you cannot access any members, right? You try something like that. P is, of course, the original pointer over there. You try the accessing via the referencing operator, the arrow operator, and try to access M. What is M? We haven't defined S yet. We can't access any fields yet because the fields don't exist. So that's going to cause an error. Weirdly, you can actually do something like this. Q equals HP. I believe you would have to give H a body. I don't think you could just get away with no body. But let's say, for example, if this takes in a value like this, and then your function, all it does is return P. Very useless function. But imagine you have a function like that. It takes in a pointer to an S, and then it returns that same pointer to an S. Right, returns it. So that would actually be okay, because P is a pointer. You know its size, 64-bit, 8 bytes. So you know how much memory you're going to have to allocate in order for H to be able to see that value. And then the return value is also a pointer. So you know that you're going to have to allocate 8 bytes again in order for the caller to see that new value. And Q is of type pointer, so it's going to have 8 bytes. There's no problems. But once again, if we try to access a member in Q this time instead of P, I mean, in this case, Q is P, but it's fine. If we try to access a member in Q, that's also going to cause an error because we don't know what the members of S are. We don't know what the elements are, so trying to access M doesn't make sense. So the only one that's kind of okay is this one. We can do a lot of declaration stuff. We can declare a lot of functions and things. But in terms of actually trying to write code that doesn't completely break, that's the only one that really works. And even then, I had to come up with a pretty contrived example. But yeah, technically speaking, what you're really asking yourself is, do I need to know the size in order for this line to make sense? And in a lot of cases, you do, right? Calling functions, returning values, declaring things and defining things. You need to know size a lot of the time. Okay. Good. This part's pretty fun. But that's on sort of how we use the struct name. Now this next bit is on structs and classes. So I talked about how structs are a basic form. Structs and classes. So I talked about how structs are a basic form of a class. What is a class? Maybe isn't super obvious to everyone, but we will see. And again, structs are a good introduction to classes. So a struct, we've seen kind of how structs work. Write it down. A struct is a class where members are public by default, right? What does that mean? Again, if you're not super comfortable with classes, that might not make a whole lot of sense, but think about the fact that we can basically access the members of a struct whenever we want using the dot operator, right? If you create a struct and then define a variable of that type of struct, you can access its members being like, s.m, if it's a pointer, you do s_m, and that lets you access the members, no problem. So in that way, we say that the members are public. There's no kind of hiding of the data at all. You can happily access them. That's not necessarily true for classes. Classes, you can actually make it so that some members or some elements can't be accessed. But a struct is a class where the members are public by default. And we can also, a struct can have member functions. So far when we've been making members or elements, when we've been making members, I've been making elements all the time, right? Int x, short y, bool likes cats or whatever. Those have all been elements, right? Variables of a particular type. But we can also have functions associated with a struct. Specifically, or including constructors. I feel like constructors are something we have sort of mentioned in passing a lot. This might be the first time we have a concrete constructor example, which is exciting. For now, I would say think of constructor as a type of function which is purely purposed to initialize stuff. Like its only goal in life is to initialize and give things values. And we've seen how we can initialize a struct just using the braces. That is not a constructor, technically. That's not a constructor. We have to define our own constructors for structs. But we've seen how we can initialize a struct without a constructor. But using a constructor is good for especially validating member arguments. I've drawn this way too small. I've written this way too small, but because I want space with the example. Good for validating member arguments, and we'll talk about what that is. So, suppose you have a struct. Let's go over here. Space. Suppose we have a struct and address, and I'm defining all sorts of things, like postcode, right, and like house number or block number. We'll say house number. House num, and street name, string street name, right? So in general, when we do something like this, in the main function, we'd say like int main, and then inside we'd go address or a or whatever, equals, and then squiggly brackets, and then we give a value for postcode, we give a value for house number, and we give a value for street name. However, we can very quickly see that there are instances where we could give a weird postcode, or a weird house number, like -6 or something. Negatives, basically. A street name, maybe we give a street name that doesn't exist, or something like that, right? So constructors give us a way of actually checking what the values are, what values have been given, or what values are wanted to be used, and we can actually check if they make sense. So how do we define a constructor? Generally, we take the name of the type, in this case address, and we make that the name of the constructor. So address, and like a function, we open up some parentheses, and we give some arguments or parameters. So we'll say like int pc, int hn, and string st or something. Little squiggly things. And then we would say something like, if PC is less than or equal to 0, or, we haven't talked about Boolean operators, but that says or hn is less than or equal to 0. That is, the postcode or the house number given into the constructor is negative, or non-positive, I should say. Then, we haven't really talked about throwing errors and stuff yet, but basically you can, like, I'll say throw a tantrum. Right? There is programmatic ways of throwing a tantrum, and that might sound like a nuisance, but it's actually quite important to make it very obvious that something has gone wrong. It's very good to make it very obvious when things have gone wrong. So we'll talk about how to do that, but essentially the consequence of throwing a tantrum means this constructor is going to get interrupted, and the address object you try to create isn't going to happen. It's going to get, because of this interruption, it's basically going to be like, okay, I'm not going to create this object, which is a good thing, because if that didn't happen, then we'd have an address object where the postcode is -10 or the house number is -30, and that could cause problems. So by throwing this tantrum and interrupting the program, like the execution flow, we kind of avoid sort of more sneaky hidden problems. Now, if we don't throw a tantrum, right, throwing the tantrum would mean this entire thing basically stops and goes out. We leave the constructor. If we don't throw a tantrum though, then we can continue on our way, and we can basically say postcode equals PC, house num equals hn. So house num from up here equals the hn given, and street name equals st. Again, the street name field in the address is being initialized to or equals the st given in the arguments of the constructor. I believe you could actually use the braces notation. Maybe I'll do that. I think you can do this instead, which I should be doing because that's what we went through in chapter 6. It's good to avoid narrowing, I guess. But yeah, so we initialize postcode, house number, and street name using the input values, assuming we haven't thrown the tantrum. So that's kind of the point of constructors. This idea that we have a way of validating input. And then once we validated it, we can assign it to our fields. Now, we talk about initialization without constructors. I think I kind of wrote this backwards. I think I was supposed to talk about initialization without constructors first. It's a bit less complex, but it shouldn't be. Hopefully that wasn't too terrible. So yeah, it initializes without constructors. So like we said, we can use the squiggly brackets. So we don't need a constructor, so we can just use squiggly brackets initialization straight up. So suppose I guess I called it point here. Imagine I have a struct called point, which is the same as the coordinate, has int x and int y. I have defined that outside the main function. And then imagine as part of my main, into main, I try the following. I try point p1, and then I do empty braces. From chapter 6, we've talked about how empty braces are used for default initialization. That is, we default the value. So if it was int x empty, x would be set to 0, or double x empty would be x would be set to 0.0, right? So the default value. In this case, assuming all your fields have default values, your p1, the fields of p1 will be set to default. So what does that mean? p1 is 0, 0, because the x was defaulted to 0 and the y was defaulted to 0. To do this, it is important to make sure that the types, all the fields, have a default value associated with them. So I think all of the basic fundamental types will, but you have to be a little bit careful with, I guess if you have more complex types, like a class or something, then things can get you have to be a bit more careful. But generally, if we're going to put empty braces there, the fields will be defaulted to their default value. What if I did something like point p2? So new point, and then I just put a 1 in there. So as you can see, we have two fields, x and y, but I've only given one value, just the one, right? Just that one value. P2 now becomes 1, 0. What happened here is the 1 was associated with the x, and then the y was defaulted to 0. The y was defaulted to 0. In essence, in order of definition, x then y, we provide values. We provide 1 to the x, and then we ran out of values, so y just gets defaulted. Right? There's no sense of it won't be the case that potentially the y gets the 1 and the x gets the 0. It's always going to be the first thing in your list, the x, is going to be given the value. And then if you don't have enough values, everything else will be defaulted. Finally, if we have point P3, and then I do 1, 2, then P3, as you can probably guess, will be 1, 2. Will be coordinate 1, 2, or point 1, 2. P3 is 1, 2. So that got the x, that went to the x, and then that went to the y. And if you were to try a third value, I believe that would be an error, because the compiler would say, I don't know where to put this one, because you only have 2 fields. So the basic rule is a compiler will fill members in the order given in the struct definition. So like we said, x and then y. Any leftover members, that is, any leftover fields here, if you don't give enough on the in the braces, any leftover fields will be default initialized, so as we talked about. Structures and arrays. Okay, so this is this follows on from this idea of trying to fill stuff up in the order given, using all the values given. So 8.2.4, and then we have structures or structs and arrays. That says arrays. Goddamn. Arrays. So there are actually two kind of perspectives you can take in terms of the relationship between structs and arrays. You can have an array of structs. Array of structs. I mentioned this very briefly in the memory alignment discussion, right? The struct layout discussion. But we can declare an array where each element is the struct, is a struct. So for some struct S, which we have previously defined, and we would have to define it so we know the size, right? We can declare something like this. So imagine we have struct S, and we have int x, int y, so it's basically the coordinate thing again. We can then say S, and then give the array name, and then give a size, right? Normally in brackets we give a size. And then we can give a particular value. These outer braces refer to the array braces. Remember when we initialize arrays, we generally have like braces on the outside, squiggly brackets on the outside. But then, to initialize each individual struct, right, because we've got 3 structs to initialize, we would use braces again. So we would say something like this. 1, 2, 3, 4, 5, 6. So just to be really clear, on the left-hand side we're saying we have some array with some name, where each element is S, is of type S, struct, and we're going to have 3 elements. We then initialize it using 3 elements, that's what that 3 is, 3 elements, of the type struct, and the first element is going to be x equals 1, y equals 2, right? We're basically doing that idea of initialization here. Then we're doing it again for 3, 4, and then doing it again for 5, 6. So we're going to get 3 structs, 1, 2, 3, 4, 5, 6. So 3 structs in the array, and the array with the array name associated, right? So that's an array of structs, and that's the way we can initialize it using the braces. The alternative way of looking at things is having a struct with an array as the field. So if we have struct with an array member. So imagine I have struct S again, then I have something like int A3. That's an array, 3 elements, each with type int. Then I have char C, then I have bool B. Right? When it comes to initializing this guy, remember, we can generally just plug in like elements, and then the compiler will basically just pass them in order to our definition. So if I have S and then like my struct, we can actually do something like this. We can say, we can do something like 1, 2, 3, character C, false. That's meant to be an array, sorry. Do it in blue because I'm lazy. 4, false, true, true, and false. So the way to think about this is, of course, the array is one kind of variable, the A is one thing, but it consists of 3 integer slots, right? There's 3 slots for integers to go. Then you have 1 character slot and 4 Boolean slots, right? Of course, 1 variable B, but there are 4 Boolean slots. So those slots are going to be filled up using this. The first slot in the array gets the 1, then the second slot gets 2, the third one gets 3. Then the character C gets the character C, and then the 4 slots for the Boolean gets false, true, true, false in that order, right? So it's this idea of like, it's almost as if like there's just buckets to fill, right? 3 integer buckets, 1 character bucket, 4 Boolean buckets, and it just fills it. 1, 2, 3, 1, 1, 2, 3, 4. There's, I guess the reason why I'm being very explicit with this is like, in my mind, I thought if I wanted to initialize an array in a struct, I'd have to put extra braces, like this, and like this, right? To really make it clear that this is my array, and this is my other array. So that's going to go to A, that's going to go to B. But you don't. The compiler's very happy to just fill up the array. You just have to make sure you're really comfortable, and it's very clear that you're filling up the spots correctly. If you miss a 3, for example, then that C is going to be put onto the end of the A array. False is going to go to C, and Boolean is going to get true, true, false, and then the last value is going to default to false. Okay, so I believe that, the compiler's going to do its best to do casting wherever it needs to. If you forget, if you miss an element, then you're going to like sort of shift your elements off by 1 spot or 1 slot. So that's the only kind of thing to look out for. But that's generally how you would initialize, using literals. All right, so type equivalence. Okay. So I guess as a bit of a callback, we talked about aliases, I think, with the using keyword in chapter 6. I'm not remembering it super well, but in essence, we talked about how you can give a type a different name, like using my int equals int. And essentially, wherever you wanted to use an int, you can now use my int. It's an alias for int. And we also said that like all types are similar to each other. The aliases are synonymous of the type they are equal to. So like if I have my int equals int and my other int also equals int using, then my int and my other int are the same thing. They both equal int, and so they both equal each other, and so they are type equivalent. You can make a variable of type my int equal to a variable of type my other int. That's perfectly fine, because they're all synonymous. That is not true for structs. Suppose I have 2 structs, S1 and S2, so struct S1 int A, and my struct S2, which also has int A. You would be forgiven if you thought that they were equivalent, or this like somehow the same thing. They both are a struct, they both have 1 field, and that 1 field is of type integer. And to really make the cosmetic similarities show, I gave them the same name. I said A and A, right? So it's fair enough to think that, well, surely, this is S1, by the way, I don't know how clear that is. S1. You might think, well, maybe the compiler has a way of sort of interpreting these 2 structs as the same thing. But suppose we try to do something like this. In our main function, we said S1x and equals 3 or whatever. If you then try something like S2y and assign x to it, this would cause problems. And at least in C++11, there is a type mismatch. Because even though they look very identical, x is of type S1, right? X is of type S1 as a struct, y is of type S2. There's no such thing as type equivalence between structs in this way. So trying to assign an S1 to an S2, even if they cosmetically look the same, is illegal. And I mean, I would hope that based on that, this is relatively obvious, but int I equals x is also a problem. This is also an error with type mismatch. The only reason why this is pointed out is because x has 1 integer, right? X is of type S1, which has 1 integer. So maybe potentially that 1 integer A will be extracted out, and that value will be given to I. But that's not allowed. You cannot make an integer type equal to an S1 type, a struct type. That's not going to work. So types are much more strict in this context than with the aliases from before. So that's that one. All right. 8.2.6 was talking about plain old data, which seemed quite innocent and not super, super scary. And then I started reading it, and then it got very, very scary. So I think my hope is that basically it talked a lot about classes and features in classes. So it was hard for me to really follow it because I haven't done anything with classes in depth. So I'm hoping after I get through classes, I can come back to it and life will make it a bit easier. But for now, I will be skipping it. So 8.2.6 is being skipped. We then get on to 8.2.7, which is to do with fields, or bit fields, if you're more comfortable, if that's easier to follow. 8.2.7, fields. Fields. Such an innocent word. So, for context, a Boolean variable, if you remember from the size thing we talked about before, a Boolean has to be at least the size of a char, and char is always 1 byte. So a Boolean usually is implemented using 1 byte, which is typically 8 bits. However, a Boolean stores a 1 or a 0, purely a 1 or a 0. Well, that's just implemented, by the way. Bool is usually implemented using 1 byte. A Boolean is true or false, so it only really needs to store a 1 for true or a 0 for false. So it might seem a bit wasteful to use 8 whole bits for that, right? In theory, we should be able to get away with just using 1 bit, because we can either flip that bit to be 1 for true, or flip that bit to be 0 for false, right? So that's the kind of context, but the reason why we generally don't do that is because a byte is the smallest addressable unit, so generally we try to avoid sort of breaking down and focusing on individual bits like that. However, although that is especially true at the in high level programming, right, where maybe trying to save tiny bits of memory isn't the biggest priority, in low level programming, it is possible to bundle several tiny variables together as fields in a struct. And aka sometimes called a bit field instead of just a field, because it's a field of bits. A struct member is a field by specifying the number of bits it occupies. And sorry, I think I said that we use this in low-level programming. It's not that like only if you're doing low-level programming this will work. It's just that you don't normally see it in high-level programming. You can technically do it if you want, but it's not necessarily the best idea. And unnamed fields are allowed. Okay. So again, it's easy to write this stuff up. It's probably more followable or more clear to show an example. So there's a very particular example given in the book. Can I get away with writing on the side, maybe? So if you have a struct, and then you call it ppn. I think it's like a very specific real thing in computing, but I'm just going to call it p. And imagine we have a field that is unsigned int f, right? And that would normally be the end of that, right? We've given a type and we've given a name. But then I do a colon, and I put 22, and then I put my semicolon. So it's a colon first, and then a semicolon. Okay, when it's 22. That's saying that this f variable is an unsigned int. Normally we would expect 4 bytes, right, which is 32 bits. I'm only going to take up 22 bits. Generally you do that because you expect that the value of the integer isn't going to need more than 22 bits. 32 bits lets you go up to like, well, for unsigned, gets you up to like 4 billion. For unsigned int, not for signed int. For unsigned int, lets you go up to 4 billion. But you reckon that you don't need to go up to 4 billion for this f variable. You reckon 22 bits is enough, which is like 2 to the 22, which is whatever. But so that's what that's doing. And then similarly, we said here that an unnamed field is allowed, so you can literally say int, give no name, put a colon, and then put 3. So what's happening is you're assigning 3 bits to nothing. You're giving it no name. You're not able to access it. You're just saying, I want to pad 3 bits, essentially. Then, using the Boolean example, we have valid, which takes up 1 bit, like we said. A Boolean, logically, only really needs 1 bit. So we have that. And then similarly, bool global also takes up 1 bit, right? So this idea of using colon and adding an integer number, positive integer number, tells us how many bits we're going to be allocating for the field, for the member. And let's close the bracket. So a field must be of type integer, sorry, not integer, must be an integral type, so char, bool, or integer, or it has to be an enumeration type, which we haven't technically looked at yet. We are looking at it in a second. I'm going to get rid of this one. Yeah, never will actually. So field must be of type integral or enumeration type. So I guess things like if you had a pointer in there, it wouldn't work. If you had a floating point number, it wouldn't work. It's interesting. I'm curious as to why you can't do it, but I mean, pointers actually make sense because every address is like the addresses are written to be 64 or 32 bits or whatever, so it wouldn't make sense to change the bits. But floating point would be interesting. So the field must be type integral or enumeration if you want to do this. You cannot get the address of the field, like we said. Bytes are the smallest addressable unit. You cannot get the address of an individual bit, so it makes no sense to get the address of global or the address of f, because getting the address of the individual bits that are being used doesn't really work. Otherwise, you can use them like other variables. Otherwise, you can use them like any other variables. Now, I don't know if I've written it. When would you use them? They are convenient for bitwise logic. Bitwise logic operators, which is mentioned at chapter 11.1.1, to extract and insert information. So, like, you think about bitmaps. Imagine, do I really want to go through an example? Again, this is like pretty, like, generally thinking about more low-level code. Imagine you have something like, well, actually, I'm doing a course in codes and ciphers, and there was a question on, like, imagine you have a deck of 52 cards, and you give someone a random number of thingies. What am I talking about? You give a random number of cards to a random person. So they have like a random, they have a hand of some number of cards. How could you represent that in a computer? One way, not necessarily an amazing way, although it's pretty good, is you allocate 52 bits. Right, there's 52 bits there, and each bit is associated with one exact card. Right, each bit is exactly. If you have the card in your hand, then you give it a 1, and if you don't, then you give it a 0. Right, so in that sense, you're able to represent the hand using 52 bits. Now, 52 bits is quite a lot, I guess. You'd think of an integer as only 32 bits, but in that sense, maybe you use a long, but instead of 64 bits, you give it 52 bits, and then you can represent it in this way, where you very specifically use just the 52 bits to represent the hand, and then, again, we haven't talked about bitwise yet, but you can basically figure out which bits are a 1, and then you can actually maybe print out the name of the card based on which bits are set to 1. So in that sense, like very quick extraction and insertion of information, right? Adding a 1 in, taking a 1 out, seeing if something is a 0 or a 1. You're able to do that quite well with a bit field. However, I didn't write it down because I didn't think it was worth. But the book does say that the slight memory efficiency you get out of this is sort of worsened or is counteracted by, or that's the pro of it. But the con is that the time of execution might be a little bit, like the speed is a bit slower because handling these individual bits is a bit more finicky for a computer rather than being able to handle sort of nicely structured bytes. Again, this is probably part of like with the memory alignment and everything. Having to deal with these individual bits is a bit more tricky to work with, and so there might be a bit of a toss-up. I'm not too sure though because it's not haven't looked into it much, but something to think about. Fields generally you wouldn't expect to see in higher level programming. All right, so now we move on to 8.3. Which is about unions. So from our introduction, we saw that unions are basically a very specific type of struct. So unions are a struct. A struct in which all members are allocated at the same memory address. So we talked about with structs, when we have a list of elements that the struct contains, usually we allocate the first element in memory, and then next to it is the next element, and the next, and the next. So this is kind of contiguous block of memory where each element comes in one after the other. With a union, it's like a struct, except you only have enough memory space for one element at a time. So in terms of the size of the union, you expect the union to occupy the space of the largest member. I'm not sure how the memory alignment stuff plays into that. I'm not sure, for example, if you have a 12-byte, something like a 12-byte element, if that sort of gets rounded up to 16 as a power of 2, if anything like that happens. But generally speaking, you expect the union to occupy the space of the largest member. And a union holds the value of one member at a time. So these 2 points kind of go hand in hand. For example, so the way we declare a union is something like this. So very similar to a struct in terms of syntax, except instead of the word struct, we use the word union. Then we would have like the identifier name, and then like braces. We might say something like int x, and we might then say something like short y, and then char c, for example. So 3 elements, right? Remember that an int takes 4 bytes typically. Y, the short takes 2 bytes. Char takes 1 byte. So in memory, this is my block of memory, we take the biggest element, in this case the integer, which is 4 bytes, and so the union itself will take up 4 bytes worth of space. So my struct, right? If I created in the main function, if I created a variable of type, of type my union, that's what it would look like. And the idea is, if I was to write, so then let's say in the main function, I say my union u, right? I declare it, and then I might say something like u dot x equals 4. Then, because it takes the whole of the 4 bytes, right, would be used to write that 4. So the 4, the value 4 would be within the whole 4 bytes. If I was to then say u dot y equals 2, right, that is the short. I'm not too sure how it would work. I'm not sure if it would take like the first 2 bytes or the last 2 bytes, but the idea is that 4 would be gone because the same sort of block of memory is being used now to write the 2. Maybe these bytes are being used to write that 2, right? And then if I was to do u dot c equals the letter L, then maybe, again, I'm not too sure which byte would actually be used, but I'll just pretend it's the rightmost. The value capital L will be stored there. But the idea is every time you write to a new element, the old one gets like overridden. It goes away. So if I was to do u dot x again, now it's really obvious that that L would have to be kicked out in order to make room for, let's say, the number 5, for that number 5 to be stored in there. So the consequence, so that's what I mean by like a union holds the value of one element at a time. Every time you do one of these assignments, only that element, x at the end, for example, has a value associated with it. Everything else doesn't have that value anymore. And that's why the union occupies the space of the largest member. If you have enough space to store your largest member, then you have enough space to store any one of your members, because you only need to store one element at a time. That's the idea with the union. And so, we already talked about this already, but as a result of these rules, it is only defined to read or use the last most assigned member. Okay, so what does that mean? We're saying here at this point it was defined to read the x value, but it was not defined to use any of the other values. Here it is defined to use the y value, but it is not defined to use the x value anymore because the x value has been overridden, etc., etc. So if at the end the x value is defined, but it's not defined behavior to try and read the c value, for example, the char, or to read the y value. It's undefined behavior. You can try it to see what happens, but there's not a whole lot of point. There's not a very good reason to try and understand what's happening when you try it, because it's undefined behavior. Something random is going to happen, and there's no documentation or any explanation as to what's happening. So it's only defined to read from the element that you last assigned something to, like this. Okay. So now, what? I guess the use case of unions, I've never had to use one before, but I guess if you ever had any reason to think that at any one point in time you should only know one of the elements, then that's when you would use a union. But I've never personally had a case like that. But now we'll look at 8.3.1, which kind of compares unions to classes. There's some pretty interesting behavior you get with unions that you might not necessarily expect. So this is unions and classes. So we had a section on structs and classes, showing how structs are kind of like a more basic form of classes. Now we're talking about unions, and all I've got here is basically a few rules. Number 1, I'm going to write this in a different order actually, but unions cannot be used as a base class. As a base class. So again, this stuff's going to be easier to understand if you have some foundation in classes. But essentially, we have this idea of inheritance, where you have a parent class where children classes can inherit certain properties from, and therefore the parent class is also called the base class, the thing that is the basis for all the other classes. So unions cannot be that parent. You cannot have a union and then have things inherit from the union. So inheritance in that sense is kind of a no-go. Second, I'm going to write the other way around. A union cannot have base classes. Okay? In the sense that instead of being it cannot be a parent class, that's what number 1 says. Number 2 says it cannot be a child class. It cannot inherit from something else. Right? Number 3 kind of follows from these two rules. A union has no virtual functions. A union has no concept of a virtual function. Has no virtual functions. Virtual functions, I think I've used them before, but it's been a minute, so I had to Google it. But in essence, virtual functions are functions that can be overridden by child classes. So the idea is, as a struct or as a class, you have a function with maybe some implementation. But the idea is, if something inherits from you, it has the option or the ability to override and redefine that function for itself. So that's the idea of a virtual function. It's a function that is allowed to be overridden by your child. But a union has no concept of that, primarily because it has no concept of inheritance in the first place. So a virtual function or an overriding function doesn't make sense. What else? Yeah. Kind of messed myself up because I've written this in a weird order. So the next point is that reference type members cannot be in unions. So for example, if you were to do something like, my union again, you're defining a union. So union, my union. And then you're going like, int x like before. And then short reference y, right? Instead of short y. The problem we have there is, well, remember that references can't change what they refer to. So if, for example, you have, int x as like, you say, my union x, whatever, and you say, sorry, not x, I shouldn't use x, u, and you say u dot x equals 4, we know that originally the number 4 will be written into that piece of memory. But then, even if it was sort of legal to do something like u dot y equals, I don't know, some short variable, pretend that we made some short s already. If we make u dot y refer to that, if we were to, again, make u dot x equal, let's say 5, that reference is basically no longer accessible, because we can't read it again, because x is the only thing that's defined to be read from, right? We can't read to y, because the last most assigned thing was the x. So we can't read the y again, and we can't like use it, and we can't reassign it, because you can't change what a reference refers to, I think. So in that way, it wouldn't really make sense to try and use references here. There might be other reasons. I'll look into it, but I think that's what I have in my little blurb here. So I'll think of that. I'll double check. But bottom line is, you cannot have references as members in your unions. What else? At most, so in a union, at most one member can have an in-class initializer. In-class meaning as part of the definition. I say in-class, but in this case, it's my unions. But basically, at most one member can be provided with an actual sort of default value. So for example, union, my union, int x equals 3, and then short y, semicolon, right? The only change I've made is I made x equal to 3 as part of my definition. So if I then do in my main function, say my union u, right, and just do that much, what will happen is the x, or u dot x, is set to 3. So in memory, there will be a 3, and the x value will be associated with that 3. That's the general idea there. But the idea is you can only have one, at most one in-class initializer. You can have 0 if you wish, but if you're going to have more than one, you've got problems, because again, only one element is supposed to be defined at any one time. So trying to do like int x equals 3 and then int short y equals 2 is a problem, because you're trying to make two values have a value. Sorry, 2 elements have a value, which you should be doing. And I've saved the biggest one for last, number 6, although it was number 4 in the actual notes. Number 6 is that a union member with user-defined constructors, with a user-defined constructor, copy operation, move operation, or a destructor, has that functionality deleted. Okay, so the reason why these sort of functionalities are deleted, right, like constructors, for example, which I think constructors are the easy one to think about, is, for example, if you have like a union like this, so you define a union, my union, you say, vector v, and you say string s, like that, and then in your main function, whatever, you say my union u, right? If we didn't delete this like constructor functionality, for example, you have a problem where, in this case, you create these fields, like these fields are associated with this u variable, and by default, if not for this 6th rule, they would both have their constructor, because they have a user-defined constructor associated with them, they would both have their user-defined constructor called and executed, which means they would both try to construct themselves. I think for a vector it would be like something like an empty vector probably, and for a string it would be like an empty string. But the concern there is you're basically trying to give a value, a default value, but a value to each element at the same time you create your u, which is a problem. So that's kind of more of an exact reason why a constructor would be deleted. But in essence, all of these operations have a risk of being applied to multiple fields at once. If multiple fields have a copy operation or a move operation, you might do a copy operation on the vector and the string, or the move operation on the vector and string, and that could cause problems. So in that sense, basically all this stuff has been deleted. So the vector no longer has its constructor, and the string no longer has its constructor, etc. So that's why they've done that. The consequence of that, I believe, is basically if you were to write this in code, I think you get an error here because the compiler will want you to write up a constructor, like will want you to define a constructor, similar to how we did it with structs. I think you would have to write your own constructor, your own destructor, things like that, because the expectation is normally these guys have their own constructor and destructor, but for us, we'd have to, in a union, you'd have to write those yourself. So there's that. All right. Last bit. So those are the rules for unions. Generally, you can see that basically the point of these rules is to maintain that idea of only one element can be held at a time. And at the cost of sort of, you reduce complexity, but that means that you kind of have some weird results. There's less flexibility. Anonymous unions. So last bit, 8.2 here, is about anonymous unions. The context in which anonymous functions is written in is to do with classes. So, and the actual example in the book is a bit, it's not too bad, it's a little bit scary. So I'm just going to give it like a quick introduction, like I'm not going to really do it any justice here. But the main thing about an anonymous function, as you can imagine, is it has no name. So if you were to create something like that, it would look a bit like this. Union, and then int I and string s. And so the idea is the same kind of rule applies of like either the I is going to be defined or the s is going to be defined, either the integer or the string, but at no point are both going to be defined. So members can be accessed without mentioning an object name. I forgot to say as well, sorry. This is an object, not a type. So normally with structs and unions, we're creating a type, which we can then associate with a variable, right? So we're creating a type. Here, this is the actual object. We've created an object in memory, which will either be an integer or a string at any one time. So I missed that at the top. So it is an object, not a type. So as soon as we've written that, that becomes the object in memory. And we can access these elements using just the element name, I or S. Again, the actual example used a class, like it contained a union within a class and then made certain methods and things, but I don't think you necessarily need a class to be able to do this. I'll double check, but my understanding is you can create that as you would with any other union, but because there's no name, that's going to be created straight away in memory, and when you try to access I and S, the same rules apply. It's just you say I and S, you don't say u.I or u.S, with a variable in front. You just straight away access the I or S, but you have to be really careful to make sure you know exactly which element is still defined based on what you've recently assigned. Alright, so that's 8.3 on unions. So we're almost done, right? We've done structs, we've done unions, now we're just on enumerations. Technically there's plain enums and enum classes, but they kind of are all wrapped around in the same section. So 8.4, enumerations. So you can think of an enumeration as a set of integer values specified by the user. So some of an enumeration's possible values are named. We give them names. It says some. I feel like basically all the time, most of the time, we use a name for our value, for the values, and we call them enumerators. The names we see, the named values we see within the enumeration, we call them enumerators. So we have two types of enums. We have an enum class, actually I think we'll talk about first. In essence, the enumerators, their names, the enumerators are local in terms of their scope to the enum. And values do not implicitly convert to other types. So what you'll see is it's sort of more scope strict and it's more type strict. More scope strict and more type strict. I was going to say TypeScript. So in that sense, you could say that enum classes are considered sort of the more safer of the two in the sense that it's more strict. Enums, he uses the word plain to like specify. Plain enums, so not enum classes, are so the enumerator names. The enumerators are within the same scope as the enum. So where you define the enum, that scope, those names are available in that scope, which is one scope above the enum scope itself. We'll see what that means in a second. But and their values can implicitly convert to integers. So the kind of notes that he has at the end of that is, in general, enum classes have fewer, he says, surprises. Easier to predict how an enum class is going to behave because of how strict the rules are. You know that nothing's going to convert into a different type. You know the scope. It's a bit more strict, which is a good thing in programming. It's nice when the rules are clear cut. All right. So talk about enum classes. Oh, I should have erased. Oh no, it's fine. 8.4.1 enum class. So we said yes, scoped and strongly typed or strictly typed. So easiest way to talk about this is using the example given. Imagine we make an enum class, right? The way this works, kind of similar to struct at the start. We say enum class, 2 words. We give the name, like traffic light, and then in a set, right, squiggly brackets, we give the enumerators, the actual names of our values, red, yellow, green. And the idea is, if you're going to create a variable of type traffic light, the values that variable can take are either red, yellow, or green. Those are the only 3 values. That's what makes enums in general quite helpful. If you have like a very specific set of values you want a particular variable to be able to take, right? Like for Booleans, you'd say true or false. But let's say but you can expand it now for traffic lights or for, I don't know, if a person is a user or an admin or a guest, like you can sort of have a specific set of values. So imagine you have one enum class like that, and then you have another enum class like warning, or warning colors, and then you have green, yellow, orange, and red, right? So you can see that the reason why this example is nice, and we'll see a bit more in the plain enum section, but we've used the same kind of colors twice. Because the scope of these colors are within traffic light, and the scope within these colors are within warning, there is no concept of like a clash, like, oh, there's two reds or there's two yellows, so there's going to be a problem. There's nothing like that, because this red, yellow, green is purely associated with the traffic light, and this green, yellow, and red here is purely associated with the warning. Obviously, orange is by itself, it's not a problem, but like it's the strong scope means these kind of clashing names don't actually clash, which is good. Now, if you were to do something like warning, I should do this in the main function. Actually, I'll make a main function to make it clear. So that's all outside the main function, and then within the main function, you might have something like this, and then you say warning. So you make a variable of type warning a1 equals 1. This would cause an error, because again, there's no type conversions. Trying to go from 1 to one of these values doesn't work. You'll see why someone might think that this could work, but for now, the idea is you cannot convert an integer back into the enumerator. If you were to try warning a2 equals simply green, again, this is an error. Each color exists within the enum class. The enumerators are not available outside the scopes of the enums, so that wouldn't work. Int a3 equals warning, and then the resolution operator, scope resolution operator, green. Again, problematic. We have successfully accessed the green value in warning. We've accessed that, but trying to cast it or convert it into an integer is problematic. There is no conversions, implicit conversions like that. Finally, if I declare warning a4 equals warning ... green, right? Resolution operator, scope resolution. This is okay, because finally we have created a variable of type warning, right? Type warning a4, and we've accessed the correct thing. Now suppose, so that's the first bit. Suppose we continue on. Imagine I have more space at the bottom. We continue on, and I try a few comparisons. So imagine I have a void function like f, which takes in a traffic light TL, right? So a variable TL of type traffic light. So imagine if I do something like if TL equals 0. Again, there's no such thing as a conversion. You're not going to be able to convert TL into an integer to be able to compare this to an integer. So this doesn't make sense. This is an error because the types don't make sense. It doesn't make sense to compare an enum class type to an integer type. If TL equals red, right? Trying to check if TL, traffic light, is equal to red. Again, this is an error. The name red is not available outside of the traffic light or warning classes, enum classes. If you want to access red, you'd have to use the scope resolution operator. What if we did if TL equals warning .red, right? Again, this is an error. We have successfully accessed a red value in the warning, but TL is of type enum class, whereas this guy is of type warning. So you're sort of comparing the wrong types again. It's kind of like trying to compare the structs, like S1 and S2. But that idea of, even if they look kind of similar, right, they both have a red value associated with them, you cannot compare one enum class to another enum class in this way, checking if they're equal. That doesn't make sense. So what you would want to do is if TL equals traffic light red. This is okay. Then you can do this check and then do whatever code you want. So yeah, we see that we've accessed the red successfully in the traffic light scope, and this is of type traffic light, and this is of type traffic light. So checking if they're equal is okay. Now talking about the integers and stuff. Under the hood, I'll erase it actually. Under the hood, the enumerators are actually represented as integers. Enumerators being the names like green, yellow, red. Enumerators are represented as integers. So like, each enumerator is represented by some integer value. So default, we typically use int as our underlying type. And by default, the enumerator values start from 0. So just to clarify, if I have my traffic light, and I have red, yellow, green again, this is an enum class, and then in my main function I say something like traffic light TL equals traffic light dot red, right? Make sure we're accessing the right scope. What's happening in memory is, well, first of all, the red thingy, the red enumerator, is associated with the value 0. The next one is 1, yellow is 1, and green is 2. So in this case, in memory, we expect 4 bytes, because normally the underlying type is an integer, which is 4 bytes. We expect 4 bytes to be allocated, and in this case, TL would be given the value 0. If we had said yellow instead, then it would be given the value 1, and if it was given green here, we would give the value of 2. Is my hand in the way the whole time? 0 if we gave red, 1 if we gave yellow, and 2 if we gave green as the value. Yeah? So the idea is, under the hood, they are integers, which is why it's forgivable to think that you could implicitly convert an enum class into an integer, or convert an integer into an enum class, because under the hood they are integers. But enum classes are strongly typed, so that conversion is not legal. You can change the underlying type. So for example, you could do something like enum class traffic light colon char, and then do green, yellow, and red, right? I would think that essentially only difference is now you're using 1 byte to represent your traffic light variables. The size of your enum class is equal to the size of the underlying type. So in this case, our underlying type is char, which is 1 byte. So any variable of type traffic light will have 1 byte worth of memory. That's the only real reason you would do this. Like say trying to save your memory. Otherwise, there's not much point because again, it's strongly typed. You're not going to be able to convert into the character, for example, because of the strong type. An enumerator can be initialized by a constant expression or an integer. Yeah. So, we've changed the default. We've changed it from default type into type char. We can also change the enumerator values. Normally we say it starts from 0 and then counts upwards 0, 1, 2. But we can actually change what values they assign to. Enum class. I'll keep the char. Traffic light. Maybe I won't keep the char. We'll say it's int. We can say that, red, instead of equals 0, we can say equals 3. Yellow, instead of equals 1, can equal 7. And green, instead of equals 2, we can make it equal 12. Right? Now, again, we don't really expect type conversions to happen because implicit type conversions are not a thing for enum classes. However, if you are planning on using the explicit casting, right, static cast int, right, if you have a legitimate reason to know the associated integer values for red, yellow, and green, in this case I don't think you would, but there might be a reason, then you can use the static cast functionality and then extract out the underlying integer representation from the enumerator. So that's when you would do something like this, is if for some reason you have a legitimate reason to assign values, and then you use static cast. You cannot expect implicit casting, but you can use static cast. I have a note here saying that bitwise operations, once again, bitwise operations are important. So if you had flags, like, again, it's hard to talk about this, but when we talk about bitwise operations, it'll make a lot of sense. But if you were to have certain flags, like, you have some number of bits, and where there is a 1 that indicates the presence of something, then maybe it makes sense to give the corresponding value on this side. Maybe you write in binary to make it really obvious, but you would then it makes sense. So enumerators, you might have flags, and that's when you do something like this. All right. 8.4.2. So we've looked at enum classes, strong type, no implicit conversions. Explicit conversions are okay, but no implicit conversions. Now we have the plain enums. How are we going for time? Okay, that's not too bad. I think we're almost done anyway, yeah. Kind of. So, the plain enums came out before enum classes. The enumerators are exported into the enum scope. As opposed to being within the enum, it has the same scope as the enum. Enumerators are implicitly converted into the values of some integer type. So before we said, implicit conversions aren't going to happen. With plain enums, they will happen. So imagine, once again, easy to talk about this with an example. And we can take the same example. And now having red, yellow, and green in both warning and traffic light becomes really interesting. So enum traffic light. Notice how I haven't said enum class, I just put the word enum in there. Then we give the name, and then we give red, yellow, and green. This would be equal to 0, this would be equal to 1, this would be equal to 2, right? 0, 1, 2. And then imagine I try something like this. Green, yellow, orange, and red equals 0, equals 1, equals 2, equals 3. This would immediately have a redefinition error. Why? Because the scope of red, yellow, green, and green, yellow, orange, red are exported to be the same scope as traffic light and warning. That is, it's basically equivalent. Writing it like this is equivalent to basically writing it outside. Basically saying int red equals 0, int yellow equals 1, int green equals 2 for the traffic light, and then again going int green equals 0, int yellow equals 1, and so on. And how I've written this. And for example, we've redefined green, and we've redefined yellow. Well, in this case, they're actually both 1, but you can't do that anyway, regardless. You can't redeclare and then redefine. I can give it a new value kind of thing. We've redefined yellow, and we'll do that for red as well. You can't do that, right? So that's a redefinition error. So that's a problem with having enumerators of the same name in your enums. So if you're going to try something like this, you kind of have to be a bit more careful about how you name your enumerators. For example, you might say TL red, TL yellow, TL green for traffic light, or W red, W orange, etc. for warning. But that can get a little bit cumbersome depending on how many enums you have. However, imagine we do something like this: void f, and again we take in a traffic light TL. If I do if TL equals 9, this is actually okay, because we can convert TL, whatever it is, into an integer. The implicit conversion into an integer is now okay because we're using a regular enum instead of an enum class. If TL equals red, assuming that we don't have warning, right? Because warning would cause us to have a redefinition error. That would be okay too. It would know to look for the red as 0. Now, hypothetically, if you were to say TL equals warning, and let's say I take my advice and I say W red instead. So let's say, I'll keep traffic light the same, but let's say warning is now W red, W orange, W yellow, W green. Maybe I should do it the other way around actually. I'll do W red on the end because I want to say something. W green and W red on the end. This is equal to 0, this is equal to 1, this is equal to 2, this is equal to 3. Let's say, for example, that TL is red from the traffic light, right? Under the hood, TL is represented as 0. Okay? Just bear that in mind. This would work out okay, even though it's two different enums. This is warning, this is traffic light, because both would be converted into their integer, right? The TL, if it's red, for example, would be converted into 0, would be implicitly converted into 0. The W red would be converted into 3. So just to clarify, this would work, this comparison would be okay, but you get false. The compiler would say that TL, even though it's red, TL red, would not be equal to warning W red. Because even though they look the same, or color-wise they are the same, in terms of integer representation, they are different, right? TL is 0, and W red is 3, and so that wouldn't work. It would be understood by the compiler, it knows what to do, but that would be considered false. But it is an okay thing to write, even though the scopes, the enums are different, because the scopes are expanded out. Sorry, not because the scopes are expanded out, because the implicit conversions can happen. And then, naturally, if we did something like if TL equals traffic light red, right? This is obviously okay. Just like before, and this would be the best kind of outcome, because it would give you, again, if TL is red, right, traffic light red, then this would give you true as you'd expect. This one would give a compiler error. A warning. The one where you compare a traffic light to a warning. This would give you a compiler warning at least, because it's saying, why are you comparing a traffic light enum to a warning enum? But it will run, like it will do the conversion as necessary. So you want to be a little bit careful. And you can specify, so just like before, we could specify underlying type. You can specify underlying type in the same way, using a colon and saying the type. And you can also give values using equal 0, equal 10, whatever. Yeah. So if you do not specify the underlying type, though, this gets a little bit low level, to be honest, but I thought it was interesting, and I'm not sure if I remember it, so it's good to try and talk it out. If you do not specify underlying type, essentially, the type is determined algorithmically. Like, in the sense that with enum classes, we chose, int was the default type regardless. It's always just going to default to int if you didn't provide a type. This one, it does its best to accommodate based on the number of enumerators you have. So, and also which values you give those enumerators. Because, for example, imagine you have an enum, plain enum, that's like, traffic light. And let's say you only have the 3 enumerators, red, yellow, and green, but one of them is like 4 billion or something, or 8 billion. I don't know why it would be, but let's just say. The reason why I choose 8 billion is because a regular integer is not going to be able to store red. It's not going to be able to represent the number 8 billion with 32 bits. It's not enough. So that's what it means by, if you don't give the type, it's going to do its best to figure out the most suitable type based on the number of enumerators you have, but also the values that each enumerator is given. Okay. So how does the algorithm work at a high level? If only non-negative enumerators, like in this case, right, all the values here are non-negative, 0 or bigger, right? So if it's like that, then choose the underlying type that can handle the range 0 to 2 to the k minus 1. In essence, where k is going to be the number of bits you need, I think. Is that right? What's 2 to the 32 minus 1? Let me check that. Hang on. Yes, I think that's right. So, k is the number of bits in essence. However, so you figure out essentially what is your biggest value, and then figure out which k value does that biggest value fit within. So making sure that 8 billion, for example, fits within this interval, and then figuring out how big k has to be, and therefore figuring out which type you need. In a similar sense, if there are negative enumerators, so instead of 26 we have negative 43, now we have negative enumerator, choose an underlying type that can handle the range minus 2 to the power of k to 2 to the k minus 1. This is, you might recognize this as like the typical 2's complement range. In essence, the way that we represent negative numbers usually allows us to represent numbers in this range, given k number of bits. So again, with negative 43 in there, we need to make sure that negative 43 can be handled in this range, and so we have to pick k to be something like, I don't know, 5 or something. Well, the 8 billion is actually not as good, but we will pick a k value that can fit everything in the range, and then choose the type accordingly. Having an 8 billion enumerator is kind of crazy, though. I don't know why you need that, but generally speaking, those are the 2 ranges you have to be able to handle, and you pick your k value in order to fit your representations, to be able to represent your numbers. And so, in that sense, we have this note that says converting from an integer to a plain enum is only defined if the provided integer is within the range. So let's say, for example, you make k equal to, so let's say we have only non-negative enumerators and you make k equal to 4, right? So that's 2, so in essence, our range goes from 0 up to 2 to the 4 minus 1, which is 15. So we can fit numbers 0 to 15 in our representation. So wait, what did I say? 2 to the 4, okay. So 4 bits is like half a byte, so it doesn't really make sense. I don't think there's an actual type that actually lets you do it like that, where k equals 4, but let's just pretend. What does that mean? That means that let's say enum. Sorry, I have an actual example for this. X equals 1, y equals 2, z equals 4, and e equals 8. So it turns out, so k equals 4 is actually the smallest k value we can use to fit all these values. If you use k equals 3, then we can go 0 up to 7, which wouldn't fit the 8. And if you go, but if you go with k equals 4, then you go 0 to 15, which can fit all these values, right? So if you were to try something like this, flag f2 equals static cast to flag, and we give the value of 5, weirdly enough, this will be represented. It won't make any sense because none of your values are 5, right? So if you ever try to compare f2, flag f2, to any one of these values, it's always going to give you false because under the hood it looks like a 5, but it will store the value 5 and will just have type f2 and it will be fine. Sorry, it will have type flag and it will be fine, right? But if you try flag f4, okay, I think there are other examples, but I only care about these two. Static cast, again, trying to cast it to a flag, but then we use 99. 99 does not exist. That's a static cast, flag 99. 99 does not exist within our range. So then this is considered undefined behavior. Again, because 15, because 4 bits isn't really a type, undefined. Because 15, for a 4-bit type doesn't exist, maybe you would have to bump up to a char, like 8 bits, which would be able to fit 99 technically, so maybe you'd be okay, but it is undefined to try and cast 99 into a flag when your range, the k value we picked, and therefore our range, only fits 16, 0 to 15. So you've got to be a little bit careful if you're going to be doing casts from integer to an enum, to a plain enum. And that's why, generally speaking, casting in general is always met with a little bit of precaution, because you don't want to do something a bit silly and engage in undefined behavior. But honestly, as far as I can tell, if you use the enum classes, generally speaking, you'll be alright. And the extra note is the size of plain enum, right? Whatever is equal to the size of underlying type, either the one that you specified or the one that was algorithmically chosen using that k and using the k thing and the ranges and stuff. All right. You can have unnamed plain enums, like the following. So 8.4.3, unnamed plain enums. So a plain enum can be unnamed. So very similar to our anonymous thingies. So like enum, we have arrow up equals 1, arrow down. Sorry, I think we'll just count up after that. Arrow left and arrow right, right? The point of this is when we need a set of integer constants, and we generally want to sort of put them in one set. When we need a set of integer constants, that's what we use this for. So again, similar to the anonymous union, you would just reference, or you would just refer to the constants without using an enum name. And again, because these constants would be exported out to the scope that the enum is existing in, then that's why you can kind of just refer to arrow up, arrow down, arrow left, arrow right without any problems. But there will be constants referring to a particular integer. So it's just basically a nice way to organize constants that relate to each other. Okay, and with that, we are done with chapter 8.